Okay, can everyone hear me? Okay. At home, can everyone hear me? Okay, great. Okay, so some people, how do I position this thing? Okay, I guess this part will be truncated. Okay, so please submit the homework before midnight if you haven't already. And as mentioned, I don't have notes, okay? Whatever notes I have are in the book. Those are better notes. So please read sections 1.4 to 1.6 of the book for today's lecture. But today I will also do an example that is not in the book and is in this lecture 2 PDF, okay? So please read that. I will talk about a random selection example, and that is not covered in the book. Okay, if anyone appears there, please, this class, let me know. And if any question appears there, please let me know, okay? So last week, I know I went very fast, but it was meant to be. So this week, there are some things that you may not have seen before in an introductory probability class. So I will go a bit slower. So we start off with X, oops. X is a non-negative discrete random variable. So I'm going to show you how to generalize whatever our discussion is to continuous case as well later on. So its sample values are in the set A1, A2, ... subset R plus. Okay. So this is a non-negative random variable, which means all the A's are, let's say, instead of this, 0, infinity. Okay. So that means that probability X bigger than 0 is equal to 1. And in particular, X can only take on these values, okay? Cannot take on others. All right, maybe I'll be more consistent and start with A0, A1, A2, okay? That's what I need to use. Now, the first part of this class is going to be on expectations. All right, expectation is like average, but there are several things that you must have seen before, but I feel that there are several things you may not have seen before either regarding expectation. So today I'm going to tell you about them. So expectation of X in the discrete case, by the way, I will write this and this interchangeably. So please forgive me if I don't put brackets. I'm very lazy. Okay, so let's say 0 to infinity, AJ, PX of AJ. This is the definition that you have seen before. Px dot is the probability mass function, PMF of random variable X. Okay, so this is something hopefully you have seen before. We say that the expectation of X exists if expected value of X is finite. Now, note that expectation values can be infinite. All right, so I repeat, this and this mean the same thing, okay? There's no loss, there's no cause of confusion without the brackets, okay? We say the expectation of X exists if it is finite. So you can have situations where expectation value of X is actually infinite, okay? But in the case where the sample values here, the number of sample values here is finite, then there is no chance of the expectation being infinite, okay? So let me show you an example. So remark, expectation need not exist if sample values or set of sample values is infinite. Okay, so the best way to talk about this is to illustrate this with an example. Probability of X equals to N equals to 1 over N, N plus 1. Here, N is in N. Okay. Okay. So hopefully people at home can still see my face, but that's not so important. Just see the thing. Will do. All right. So here, this is 1, 2, all the way natural numbers. Okay. So we can check. First, we need to check that this is indeed a probability mass function, that is sum of Px equals to N. You take the sum. This is equal to 1. Homework check, all right? I'm not going to check this. I'm going to check that this has an infinite expectation. So let's try to compute the expectation value of X. we have this formula n probability x equals to n, right? But you see the n and n are going to cancel. So you're left with this thing here. And this is the harmonic, roughly speaking, is a harmonic series. So it is infinite. Okay, so there are situations where the expectation can be infinity, but this is necessitated by the fact that this must be infinity here. There must be an infinite number of values that x can take on. Otherwise, there is no chance. Okay, this is a little bit annoying that I have to stand up like that, but it's okay, right? All right, so now I want to tell you some interesting fact, okay, that you may or may not have seen before. Fact, okay? So this fact has a name. It's called layer cake. It's not in my notes. Representation. And some of the things I write today may not be in my handwritten notes. And we'll see why this is called layer cake representation. It's like a cake, you know. Later I'm going to show you why. Okay, so the fact is the following, all right? The claim is that x, okay, now the x is a non-negative discrete random variable, okay? That is, I've already said that at the beginning. We are not going to write this again. Non-negative discrete random variable for now, okay? So the fact is the following. This can be written as 1 minus integral of 1 minus fxx dx, where it is a CDF, where fxx is CDF, oops, df of x, okay? So, oh, this is quite strange. You see, the first time you see it's quite strange. Because, you know, the vanilla definition of expectation value of x is just what I showed you just now, x pxx. Right, that was the vanilla, that was the standard definition of the expectation. Now we involve this object here, okay? By the way, Gallager's book, if you read it, they call it fxc like this. This is what Gallager's book does, but let's write it up in its full glory, okay? So this is what Gallager's book writes. Now I just want to remind you that fxx is the probability that x is less than or equal to x. Okay, this is the CDF. So we are able to relate. We're able to relate the CDF to the expectation. Okay, so this is called a layer cake representation. So we're going to prove this. And the proof will expose why this is called layer cake. All right. So everything here we have defined before. All right. We have talked about the CDF, cumulative distribution function. We have talked about expectation. You would have learned expectation in your undergrad probability, but this is a different way of writing it, and we will see that this is useful. So proof. Okay. First, we ask the question: what does the CDF look like? For a non-negative discrete random variable x that takes on values a0, a1, a2. Now my proof is only going to be for a special case. All right, I don't want to be too ambitious. Let's say we special case up to 3 only, a3. Okay, and furthermore we set this to be 0, r plus. Okay. R plus means the set of all non-negative numbers, okay? R plus plus, sometimes I use, is a set of all positive numbers. Now, say A0 equals to 0, less than A1, less than A2, less than A3, without too much loss of generality. I'm going to prove this small case, this simple case only, all right? So let's see, so the question is, what does the CDF look like for this? This should be a question mark here. So let's go and draw a picture, okay? This is A0, this is A1, this is A2, this is A3, this is X, this is fxx. Okay, so this is, I'm going to draw a picture here. If you recall, the CDF is right continuous, so this is empty here. And we're going to label this properly later on. So this is this. Maybe here jump very little. And here we are going to jump up to 1, finish. Okay, so let us label all these jump points. What color do we like? This color, all right? So this jump point is P of A0. This is P of A1. This is P of A2. This is P of A3. Okay, by this, I mean this length here. Okay, and of course, this goes up to 1 and continue. Okay, so Everyone understand? So this is a standard CDF. It's the probability that x is less than or equal to x. Maybe last time we drew a similar picture. Maybe we drew a picture for continuous case, but I think I also drew a picture for discrete case. So this is the CDF. Got it? Any questions? People at home can hear me? Can people at home hear me? Yeah,
Yes.
good. Okay.
Yes, we can.
So now let's draw another picture. Okay. Another picture is the following. 1 minus fx of x. Okay, so that's not very difficult, right? You just take 1 minus everything. Okay. So let's do this carefully. Right. So we're just going to use red again. And okay, what is 1 minus? Right now let's say, oops. Oh man, I touched it. Yeah, okay. Okay, so now let's do this meticulously. Now let's consider this particular point here. This is 0. What is 1 minus 0? Is 1. So we start off with 1 here. Okay, and then we have a solid here. Oh, sorry. So here it says solid. Yeah, I think there's something wrong there, but never mind. Small issue. Okay, then here, okay, then we go up to A1. All right, so what am I doing? Right, so here, what I'm doing is I'm subtracting P of A0. So here, P of A0 here. Understand? So I'm just taking 1 minus this part. Now I'm going to take 1 minus this part. Okay. So what I'm going to do is I will have this solid here, no solid, go there, solid, down, and go there, solid, down. Okay, so let me just put all these lines properly, and let me use this red. This is A3, A2, A1, and 0. Now let me label all this properly. We're just flipping this around. P of A1, P of A2, P of A3. Sorry, it's very small, the handwriting, but hopefully you can see. Can see? Right, so yeah.
I think the solid
Flipped. Okay, yeah, sorry, flip. So my notes are actually correct. And I'm overthinking here. Thank you very much. So let's get rid of the solids here. Okay, and let's do this one more time. So this should be solid. This should not be solid here. Over here, solid. This should not be solid. This should be solid here. Not solid here, and solid here. Okay. All right. So maybe this is just a plot. You can just verify this carefully. Okay. So we're just flipping this around. Okay. Now let us calculate this object 0 infinity 1 minus fxx dx. So now I've meticulously drawn this graph here, right? So this function here is drawn here. So what am I doing? I'm going to calculate the area under the graph here, because that's the meaning of integration. Integrate from 0 to infinity of 1 minus, by the way, this has a name, complementary CDF. Okay, this has a name, complementary CDF. 1 minus of the CDF is complementary CDF. So let us calculate the area. This is the area under the complementary CDF from 0 to infinity, right? So now let's draw this pictorially, okay? Let's calculate the area. Let's calculate the area like this. Now you can calculate the area in various ways, but let's just calculate the area like this, okay? So what is this? What is this area now? This area that I just highlighted is width times height, right? So it's this width times this height, right? And it's just nothing but A1 times PA1. So this rectangle here has this area. Can you see? That's the PA1 is the height, A1 is the width, right? Okay, continue. So now let's talk about this rectangle here. This is A2, PA2, right? Now let's talk about this big rectangle here. Okay, it is A3, PA3, right? Everyone understood? People at home understand? Okay, so we have that this is equal to A1, PA1 plus A2, PA2 plus A3, PA3, which is equal to, we can write it as sum I running from 0 to 3, I, PAI, PAI. Sorry, it's very ugly, but this is the way we learned expectation value of X, as proven. So this is a proof by picture. Okay? Proof by picture. Any questions? Okay. Any questions? So basically, I just calculated the area. Oops. Basically, I just calculated the area of the complementary CDF. Okay? And the area then turns out to be this A1, PA1, A2, PA2, A3, PA3, which we can summarize in this way here, because A0 is equal to 0. Okay, so A0 is equal to 0. So this quantity here is nothing but the regular expectation that you have learned before. Okay, so this is a proof by picture. Okay. Okay, so let us just write this here so that it's neater. So that's a proof. Now, here's another fact. Okay, for we can rewrite this as follows. For a non-negative integer valued random variable X, okay, we can rewrite this as expectation value of X equals to the sum n running from 0 to infinity, probability of X greater than n. This is equal to sum probability that X is greater than or equal to n running from 1 to infinity. Okay, so this is the second fact. I mean, this is a matter of bookkeeping. All right. So we just prove this equality here. Okay. All right. So, oh, by the way, I wanted to tell you why this layer cake, right? But I don't even need to tell you because you look at this. Doesn't it look like layers of a cake? So this is known as the layer cake representation of a function or of a F expectation. All right, because basically what we are calculating is in fact the layers. We are summing up the layers of a cake. All right. Okay, so we are going to prove this second fact. So we're just going to show the following: n equals to 0 to infinity. We can recover the usual definition for expectation. So this is probability X bigger than 0 plus probability X bigger than 1 plus probability X bigger than 2 plus so on. Okay. So this is nothing but we can group this together. X, what is the meaning of X bigger than 0? X bigger than 0 means that X can be 1, 2, 3, 4, 5. Okay. So we can write this as P of 1 plus P of 2 plus, let's be a bit more careful here. P of 3 plus dot dot dot. So that is this term here. This gives rise to this. Okay. And plus, okay. Now what is the meaning of P of probability of X bigger than 1? This term here. That means that X can be 2, 3, 4 onwards. It must be at least 2, right? So this is P of 2 plus P of 3 plus so on and so forth. So this term here is equal to this sum here, right? I'm going to do this one more time only. Okay, so this is plus 0. What is the meaning of probability of X bigger than 2? That means that X can be only 3 onwards. 3, 4, 5. 3 plus P4 onwards. Right? So if you see this, how many? Let's see, this is, okay, this purple part comes about here, purple part. Okay? So how many, just to make this nice, okay? This part is the yellow part, okay? So now we are going to sum vertically. Okay? Now we're going to sum vertically. So this is going to be what? 1 times P1, because you only have one copy of P1, 2 times P2, right? plus 3 times P3, and you see the pattern. Okay, so this is sum n, probability mass function evaluated at n running from 1 to infinity. Okay, this is nothing but expectation value of x. Okay. Now, here I did say something, if you are careful. I did say that x is a non-negative integer valued random variable x. Non-negative, it means that it can be 0. Okay, but here I somehow cheated. I started from 1, right? But this can be rewritten as sum n from 0 to infinity, px of n, because 0 times anything is 0. So this is the vanilla definition for expectation. Got it? So we have proved a couple of facts. I mean, these two are actually equivalent, right? Both are the layer cake representations. Okay. At least for discrete, we have proven a different representation for expectation. Okay. So then you may wonder, right? Am I cheating? Can we do the general case? Right. I wanted to build up the difficulty. First, I drew a picture. Then I do the integer value representation, integer value result. Fact. Now this is not in the notes. Okay. This is not in the notes. Let's see whether I can do it. Okay. Let's write down the facts. This is not in my handwritten or anywhere. Okay. So let's say x is a continuous random variable supported on the positive axis. X is a continuous random variable, and probability of x bigger than or equal to 0 is equal to 1. So we don't allow for negative values. Then expectation value of x can be written in two ways: fxx 0 to infinity dx, and it can also be written as the complementary CDF. Okay, so fxc, all right, is basically this is Gallager's. Okay, fxc is 1 minus fxx. General case, continuous random variable. So we cannot really do this layer cake chopping up technique. But maybe if you are very careful, you can quantize or discretize in some way and do it. But let's do a more direct way. Let's do a trick. Okay. Let's consider a trick. Actually, it's not a trick. It's just a matter of integration. So we're going to prove this. We're going to prove this equality here. Okay. So let's consider the right-hand side. This requires a little bit of integration gymnastics. Okay. So this is a probability. What is the complementary CDF, right? This x bigger than x dx. That's the right-hand side. Okay, because the CDF is less than equal. Sorry, here I'm skipping one step. Hopefully you all can, people at home are accept this skipping one step. Okay, so now we can rewrite this as follows, because you see, we have to introduce the density here, the probability density function. We have to introduce a probability density function, so we better introduce it. So how do we introduce it? Okay, what is the meaning of probability x bigger than x? That means we integrate from x to infinity of the density du dx. This part here is the probability part. What can we do next? It looks very difficult, right? But we can introduce our favorite trick. Not our favorite trick is some trick. I don't like to integrate from x to infinity. Can I integrate from 0 to infinity fx of u? But this is not correct, right? Because we need to compensate in some way. You're only integrating the u's that are bigger than x. Maybe exactly bigger than x. Say, oh, this continuous is okay. All right? du dx. So this is called the indicator function. This is called the indicator function. And we will frequently be using it. Fn is function, okay? And it says that if the clause inside is true, then that function takes on the value 1. If that clause inside is not true, that function takes out the value 0. So let's see whether it's correct. If u is bigger than x, I will return. If u is bigger than x, I'll return 1. And that dovetails with the integration range here. If u, however, is smaller than x, I return 0. Okay, understood? Now, this is an integral. This is the x integral. X going from 0. This is the u integral, right? U running from, from 0 to infinity. So now I'm going to swap these two. Even though they don't look different, right? Let's just take note of the u here. Let's just take note of the x here. Okay, fx of u, 1 u bigger than x, dx du. So I move the x inside. Okay, you allow me to do that? Who allows me to do that? This is not always possible, you know. All right, this is not always possible. But then Fubini allow me to do that. You don't need to know this. Or sometimes people call it Tonelli, same idea. All right. So now you see, what am I going to do? Why did I copy? Because I don't want to write so much. Because now this guy here, this guy in yellow here, has got nothing to do with x. You can bring it outside. Right? So that's what I'm going to do. I'm going to bring it outside. And I'm going to integrate from x equals to 0 to infinity here. Okay? Right? Agree? We can do this because this is nothing but a constant with respect to x. All right? So now we focus our attention on the inside here. This looks very strange. Okay? What are we doing? We are looking at a certain function in x. All right? And what does this function look like? I mean, this object here. This object here. What does this guy look like? Well, can we graph it? All right. It is 1 when x is smaller than u. And 0 elsewhere. Okay? This is 1. So this is the function. This is the function 1, x smaller than u. I'm writing in this way, okay? U bigger than x means x smaller than u. Right? So what is the integral of this business here? Area under the graph here. What's the area under the graph here? What's the area here? U, right? So now this object here in red parentheses is u. And so you can collect everything together, u, fx u du, which is the left-hand side. Okay? So this is the general result, okay? This is the general result that allows us to conclude that the expectation value of x can be written as the complementary CDF. Okay? So you learned before for continuous random variables, okay, that expectation value of x is x fxx. Okay, this is standard thing from undergrad. So the first step is, okay, let's look at the right-hand side. Let's recall the definition of the CDF and hence the definition of the complementary CDF. Now, surely we need to introduce the PDF, right? Because the answer has the PDF here, right? Surely we need to introduce it. So we introduce it in this way. This means the probability you're integrating the PDF from x to infinity. Okay? So now this is the main trick. We introduce the indicator function. We introduce the indicator function because I don't like this triangle range. If you draw this out in 2D, it's a triangle, all right? But I don't like this, so we introduce this. This truncates the integration from 0 to x, okay? Now, this is both a function of u and of x, right? This indicator is a function of both u and x. Now, I swap using Fubini, right? You don't need to know what's Fubini, really. You are allowed to swap in engineering. So swap, all right? The u is outside and the u becomes outside here. So now we have this, but this is a constant with respect to x, which is the inner integral. So I can bring it outside here, and I'm left with this inside thing. And this inside thing, by using this picture here, I see that the integral of the inside here is exactly u, and we are done. Okay? Maybe I write this way. So that's the general proof. Any questions? Sorry, in a regular semester, when I have more board space, you can see more things. But this is the only thing you can see now. Everything here inside is non-negative. So there's no cancellation. You can do Wikipedia of Tonelli theorem. Tonelli is probably the right thing. Fubini is more general. Fubini says the inside must be L1. The thing inside must be L1, but here non-negative is fine. So there's no cancellation. Any other questions? Very good. So many people show up. I'm not talking to an empty Zoom thing. How many people are there here? Oh, so many. Okay. Any questions? All right. So we want to generalize this a little bit. So this everything we've done up to now is for non-negative random variables, right? But generalization to non-negative random variables is not so difficult. But I'll restrict myself to the discrete case. Okay. So if x is a random variable, discrete has both positive and negative sample values, then what happens? Okay, so x belongs to, the sample values of x take on A1, A2, and so on and so forth. Okay, then we know that the expectation value of x from undergraduate probability is AI, PAI. Okay, P, when I write P here, I really mean P sub x, okay? So I'm going to be very lazy very soon. So this can be split into two parts, AI less than equal to 0, AI P of AI plus some AI bigger than 0, AI PAI. Okay? In fact, this can be expressed, we will shortly show through picture, in terms of the CDF of x, fxx. Okay? Now, we are going to show this for a very restrictive case of A1 less than A2 less than 0 less than A3 less than A4. The general case follows by the same type of arguments. In fact, right, for any function x, because random variables are functions, all right, for functions from the sample space to R. Now, this is a general recipe when we deal with functions, right? We like to deal with non-negative functions first. Then once you have dealt with non-negative functions, the generalization to non-negative functions is usually easy because you can always write a general function that takes on positive and negative values into two parts, x plus and x minus, all right? Where x plus is equal to the max of x and 0, and x minus is equal to the minimum x minus x and 0. I think there's a minus here. So there's a positive part and a negative part. I'm not quite sure whether this is correct. This x plus is definitely correct. All right. So we want you basically extract the positive part and the negative part, and both of them are non-negative random variables now. You try to create non-negative random variables. So all these things are non-negative, and we can work with them in the usual way. All right. But we're not going to do this. We're not going to do this in this way. Okay. We're just going to draw a picture. Okay. So we're going to draw the layer cake representation picture again. So let's try to be clear. So here we have, we are going to draw the following. Here's X, here is A3, A4, A2, A1, okay? So now on the left-hand side here, I'm going to draw two graphs here. On the left-hand side, I'm going to draw the CDF. On the right-hand side, I'm going to draw the complementary CDF, okay? And we'll see what happens. So the CDF is easy to draw because I'm very familiar with it. It's just right continuous, that's the key. Okay, that means the dot is there. Okay, and then we go here. So, and then we do here. Maybe we do dotted here. and we do dotted here, and this is solid here. Hopefully I get the solids right. But here on the left-hand side, I'm drawing the CDF. Okay. Maybe this is solid here and solid line here. Okay, so what am I drawing? Let me label this properly. Okay, what is this jump? This is P of A1. This is P of A2. These are the jumps. I'm just drawing on the left-hand side the CDF. And on the right-hand side, I'm drawing the complementary CDF. Okay. Okay, and so on and so forth. And this is what is this jump here? This very ugly. This is A4. This should be the correct color. Sorry. Not so easy to change color. P of A4 and this P of A3. The right hand side should be clear. We have done this before. Okay, this is the complementary CDF. So now let us, okay, so I've drawn two curves here, right? I've drawn two different curves here. Okay, so let us consider the following. This is the claim. Expectation value of x is equal to the integral from the negative part minus f of xx dx plus integral from the integral in the positive part 1 minus f of xx dx. Okay, why is this so? Okay, now when we look at the layer cake representation here, let us consider this height here. How much is this height? It's P of A4. P of A4, right? This P of A4. Now, what is the area of this rectangle here? All right, this area of rectangle is nothing but A4 P of A4. This rectangle here. And this rectangle here is how much? Okay, P of A3. A3. Okay. Now, we also want to calculate the area of this rectangle here. Oh, I'm sorry, this rectangle here. Okay, but here we have to be careful, right? Because the A2 is over the other side. What's the area of this rectangle? A2 is a negative number, you know. A2 is a negative number. Area cannot be negative. So the area here is minus A2P of A2. Minus A2P of A2 is a positive number. Okay, let's get rid of this line here. Now let's calculate the area of this slice here, this layer here. This slice here is A minus A1 P of A1. Understood? So the area, so this takes care, this minus here takes care of these minuses here. You are taking the area, the negative area under fxx. It's very counterintuitive, right? This is what is the area under fxx on the left side? What's the area of fxx on the left-hand side? It is nothing but, okay, the area on the left-hand side of fxx dx is nothing but a1p a1 plus a2p a2, right, minus minus so a1. The area of this guy here is minus here, right? Yeah. So what happens here is that the expectation value can be written as follows, where we need to take into account this minus sign here because the A's are negative over on the left-hand side. All right, this whole thing can be summarized into the following: u of x minus fx of x dx. Okay, where u of x is the Heaviside step function, it's just a step function here, is 1, 0, x bigger than 0, and x smaller than 0, right? Because when x is smaller than 0, this takes on the value 0, and you recover this part here. When x is bigger than 0, this takes on the value 1, and you recover this part here. So this negative sign is to take into account the signs of these two things here. Okay, so this is the general formula for expectation in terms of the CDF, which you should know. Okay. So we say that for a general, not necessarily discrete random variable, not necessarily non-negative random variable. For a general random variable x, expectation value of x exists with the value given in star. Star. Okay, what is star? Star is this one. If each of the two terms is finite. By each of the two terms, I mean each of the two integrals. Okay. Now, the integrals need not be finite. Okay. Like I've shown you one example where the random variable is non-negative and discrete. It's a special case of this, in which the integral is not finite. Okay. At the very beginning, I showed you this. Maybe you can do this. Here. This one here. The integral on the right-hand side will not be finite, because this is exactly the integral on the right-hand side. Okay, it will not be finite. So we say that the first moment or the expectation does not exist. All right. We want to deal with random variables for which the first moment, or actually all moments, exist. Then things will be interesting. Okay. So that's the whole story behind expectation. The only subtlety here is that we need this. Okay. We need this minus sign here. Otherwise, it's probably everything here is clear. You can prove this from picture, or you can prove from some integral gymnastics expressions here. Okay. Right. So I just want to make this a bit clear. Maybe this is a bit confusing. All right. So what is this? What is this left-hand side term? This thing in brackets. This is A1PA1 plus A2PA2. Right? Why? Because the integral over on the left-hand side of the cumulative distribution function is equal to minus A1PA1 minus A2PA2. Okay, so the minus of this f is the sum A1PA1, A2PA2. And of course, here you already know is A3PA3, A4PA4. So the sum of these two things here, gives you the regular expectation. This thing here is the regular expectation. Understood? Okay, so you see here, this part here, with the minus sign, you get rid of the minuses here. Because the integral from minus infinity to 0, you need to insert these minus signs. So here you negate these minus signs, you get this thing here. And this is regular. We have already shown this. So this entire thing inside the orange blob is nothing but the expectation for a regular discrete random variable with 4 values. Okay? All right, so now I want to talk about other things. Any questions about expectation? So you have probably learned about expectation from undergrad, and you write it like this, AI, PAI, or some integral expression, fxx, this sort of thing. Today, we learn another way of writing expectation in terms of layer cake representation, right? In terms of the cumulative distribution function, which will turn out to be useful later on when we talk about some other applications in stochastic processes. Okay, so let me get rid of all these things here. So now we're going to talk about other expectations, okay? Then we'll talk about properties of expectations. So random variables as functions of other random variables, okay? So if I give you a random variable, you can create another random variable. So x is some mother random variable. And let's consider a certain function h going from R to R. So we can then define a new random variable y, which is a function of x, and the function is h. Okay, so we can create a new random variable. So So this is undergraduate probability. Fact. The fact is that we can evaluate the expectation of this new random variable y in several ways. One is, okay, let's consider expectation value of y. Okay, you can do the following. Say everything continuous, okay? dy, okay, that means integrate over all r. So this is one way, right? So how you do this? You first find the PDF of y, and then you integrate. How to find the PDF of y? This is an undergraduate thing that I will not go through. Okay, you have a random variable x, you want to find you have a new random variable y that is a function of x. The random variable y will have a new distribution. How to find this new distribution? I'm not going to discuss this. I do not know whether there are some exercises, but you should know how to find this new distribution. Okay, so this is one way, the vanilla way, the standard way, plugging into the definition way. Of course, today we learn another way, which is the layer cake representation. Or say this is non-negative, right? Then say non-negative random variable y. Then we can write this as greater than y dy, integrate from this to that. Okay, so this is another way of writing, but this is not the point I want to make. Okay. Now there's a shortcut way that does not require you to find the distribution of y. So you can just do the following. All right, x. Okay, you can just do h of x, fx of x, dx. All right, so these are two equivalent things. Hopefully you've seen this before. Okay. So I just want to remind you of these things. Some functions, however, are more important than others. So this h is some generic function of x, right? But we want to care some functions more than others. All right, so for example, if h of x is equal to x to the k, then expectation value of y is equal to x to the power k fxx dx. This has a name, kth moment of x. So the first moment is the mean, the second moment is the second moment, the third moment is also very important, and so on and so forth. Okay, so now we can create a new function h of x is equal to x minus x bar squared. X bar is the first moment. So here I can create this function. Now this is a function of x only. X bar is a constant. Okay, so this is an interesting function that leads to the following. Expectation value of y equals to integral of h of x fxx dx integral over r. This is x minus x bar quantity squared fx of x dx integral over r. Okay, this can be written as expectation value of x minus x bar squared. So this is the first moment of the expectation. Okay, and so now we have created a new function, right? The new function is h of x equals to x minus x bar quantity squared. Now I've created a new expectation. This has a name. This is called the variance of x. Now the variance of x is not the same as the second moment. Okay, the variance of x is not the same as the second moment of x. This is the second moment. But one can show very easily, exercise, that the variance of x is related to the second moment in the following way. Okay, in particular, if x bar is equal to 0, that is the first moment is equal to 0, then we clearly have that these two are the same. And we don't have to take away the extra part. So this is some small exercise. This is just a reminder about variance, expectation, so people at home understand. But maybe this thing you don't really understand. Okay, let me show you some fact. Okay, let's say we want to minimize, we want to consider this optimization problem. Over all possible x in R, expectation value of x minus x squared. Okay, So you can think of this as some engineers call this mean squared error. Engineers like to call this mean squared error, okay? Now, so which is the deterministic value of x that minimizes the mean squared error? Well, it's easy to prove that the value, not enough space. The value of x, still not enough space, that achieves this is x bar equals to expected value of x. So the value of x that minimizes the mean squared error is exactly the expectation. How to prove this? Differentiate, set to 0. So you think of this as a function of x, say g of x, and you differentiate with respect to x set to 0. So you can take differentiate with respect to x of this guy here. Okay, this x is uppercase, this x is lowercase, okay? Sorry. So you can differentiate the expectation. You set expectation 2 of x minus x equals to 0. So now you can take away this 2, okay? And this x is deterministic, so x must be equal to expectation value of x. After you set this to be equal to 0. So this is the connection between mean and variance. This is the connection between mean and variance. And actually there's a much deeper connection here that we may talk about later on when we talk about conditional expectation. Okay? Any questions? Any questions? So I want to say you need to read this part, okay? Whatever I talk about is here. And in, and lec2.pdf. Part of it, all right? Not everything. Read this, okay? So, any questions? We don't need to hurry. We are in good time. We really don't need to hurry. You know, today I want to do a proof. And when I was in school, when I was in like your age, then I had some professors, and they said that you cannot do a proof halfway. So you cannot do a proof halfway and stop. Then the students will not be able to connect the whole proof. So I want to do a big proof in the middle. So I do not know where's the optimal point to stop, but it's certainly not now. So let's continue. So, all right, another function of interest is h of xy equals to x plus y. Now this function is a function of two things, x and y, okay? So just now that function was only a function of one object, but nothing is stopping us from making a new random variable z, okay? We can make a new random variable z from x and y. There's no harm, right? So now I'm making a new random variable z that is equal to x plus y, okay? So z equals to h of xy equals to x plus y. Let us try to understand this object. Okay, so if x and y are independent, this means independent, okay? We can express the distribution of z in terms of the distributions of x and y. And by distribution, I really mean the PDF. Okay? So this means the same thing to me. So let's do this. All right? And this is going to remind you of undergrad probability. So let's start off with fz of z, CDF of z. What is the meaning? z less than equal to z. Okay, so this is nothing but the meaning of cumulative distribution function of z. Okay, so now this is nothing but probability x plus y less than equal to z. Right, I'm plugging in just x plus y. Now we do the following. Integral of f of x, probability x plus y less than equal to z, condition x equals to x dx. Say minus infinity to infinity. Okay? This has a name. You may have come across this. Law of total probability. Okay? So these are some things in undergrad probability that we have to know. Law of total probability. That means we can compute a probability by conditioning on all constituent events. The events are x equals to x. And the probability that x equals to x is this amount. Okay, so I'm just chopping up the sample space in terms of x. Okay, so now I know that I've conditioned on this event here. So x here becomes little x plus y less than equal to z. This is little z, condition x equals to x dx. Right, because I know that I'm living in a world that x is equal to little x, so I can replace. Right, so I replace x upstairs here. I replace the x upstairs here with the x down here. Now it becomes small. But what can I do? What can I do now? Okay, I can throw this away. Why can I throw this away? Why can I throw the magenta, the purple part away? Because very good, x and y are independent, so we can throw it away. Okay, so let's throw this away. And the reason why we can throw it away is because x is independent of y. Okay, where are we now? Oh, here. So we have integral fxx of probability y less than equal to z minus x dx. Right, so this is a matter of tracking definitions. I mean, this is nothing, this is moving around. But this is nothing but we can express in terms of fxx, capital F. This is the cumulative distribution function of y evaluated at z minus x dx. Okay? So let me go through this sequence of steps again. We are not done yet. So here, we want to calculate probability that x plus y less than or equal to z. And x plus y is exactly equal to random variable z. Okay? This becomes this law of total expectation. We condition on x equals to x. Basically, we cut up the sample space into many pieces. Okay? Now here, we replace the capital X here with the little x here. Right? Because we are conditioning on this event. By independence, we can drop this part. So we drop it entirely. We move this x over to this side here. Now we realize that this is the cumulative distribution function of y. So we write down here. Okay? So all in all, what have we shown? We have shown that probability, or rather, what do we start from? We started from the CDF. Fz of z is equal to this. We have shown this. We are almost there. We wanted to, what was our goal? Our goal was to relate the probability density functions of z to those of x and y. But this is not quite, because this is the cumulative, and there's a cumulative here. All right. So differentiate both sides with respect to z, all right, to obtain This is the PDF of Z equals to Fz prime of Z equals to the entire thing prime with respect to Z. Maybe I shouldn't do prime. This is very analysis thing, but this is d by dz of Fzz equals to d by dz of this thing here. Correct? Right, so I'm not cheating because I just copied this. All right, so now we can rewrite this as follows. Take this thing here. What am I going to do here? I'm going to move the derivative inside. So I'm going to move this right up to here. Okay. Why can I do this? This is called in mathematics differentiating under the integral sign. Maybe you've heard of it. You're differentiating under the integral. Okay, these two objects, differentiation and integration, are linear. So at a first glance, it's okay. At a second glance, you need a bit of conditions on the things inside, on the integrals, integrands. These are the integrands. Okay. Now let's assume that we can do this. Then we will have to differentiate this with respect to Z. This is the differentiation with respect to Z. Okay. So let's d by dz of Fy of Z minus x dx. And we are done. Fxx, this is Fy Z minus x. Because we are differentiating with respect to Z of this respect to this argument of the cumulative distribution function of Y, we get the probability density function of Y as desired. What is this? Oh yeah, how to do this? How do I get rid of this now? I don't know how to get rid of this. Okay. Okay, good. So what we proved? Theorem. If X and Y are independent, then the PDF of Z equals to X plus Y is this. Is given by Fzz equals to this. And this has a name. If you are electrical engineer, you would have come across this name before. It's convolution. It appears in signals and systems and everywhere of Fx and Fy. It's a convolution of this. So Fz is equal to the convolution of Fx and Fy. So this is the convolution formula we have proved. Okay. So in particular, independence is crucial here. We are making use of independence in a very crucial way. We are not dropping anything. Okay. So that is the formula for the sum of independent random variables. Now this is very complicated. All right. No one does it this way. In practice, we do what? What do we do when we want to find the distribution of Z equals to X plus Y? You wouldn't plug the densities into this formula. You would do what? Fourier transform or Laplace transform. You will go into the transform domains or moment genting function. We're going to talk about this later on. Okay. Going into transforms domain makes life easier because instead of convolution, we are doing multiplication. Okay. But maybe you have seen this before, maybe not. Don't worry about what I said. Okay. All this is in the book. Okay. So some important relations. Fact. For arbitrary random variables x1, xn, arbitrary, so not necessarily independent. We have expectation value of x1 plus ... plus xn equals to expectation value of x1 plus xn. This has a name. This is called linearity of expectation. Cool. Arbitrary. So this is very crude. This is very simple to prove. Homework, okay? I feel it's very simple to prove. But later on, we are going to prove a deep result using linearity of expectation. Okay. In fact, later on, we are going to do exciting theorem later on using linearity of expectation. Okay, for x1, xn, independent. Actually, this is not quite true. Uncorrelatedness is enough. Uncorrelatedness is enough for this fact. What's the meaning of uncorrelated? That means expected value of xi, xj equals to expected value of xi, expected value of xj. That's the meaning of uncorrelated. Okay? That means the covariance is equal to 0. The covariance is the difference between these two things. Uncorrelatedness means this. But by independence, independence implies uncorrelatedness. Now, because if these two people are independent, then the expectation of the product is equal to the product of the expectations. But this is the definition of uncorrelatedness. So independence implies uncorrelatedness, but not the other way around. Okay? But here's a fun fact. If everything is jointly Gaussian, independence and uncorrelatedness are the same concept. Only when, or not only, but I'm not sure whether it's only when, but if x1 to xn are jointly Gaussian, independence and uncorrelatedness are the same concept. Okay? All right, so where are we? If x1 and x1 to xn are independent, actually uncorrelatedness is enough, then variance of the sum, maybe let's make it more general, okay? It's not in my notes. Say alpha I xi is equal to what? Sum alpha I squared variance xi. Okay, so this requires a small proof. This requires a small little proof, I think homework. Okay? So actually uncorrelatedness is enough. This is algebra. How would you prove this? Proof sketch. Say, oh, I'm very lazy. Say I'm going to do 2 and all these are equal to 1. I don't even want to do this. All right? You generalize it. Variance x1 plus x2. Okay? Say also the means are equal to 0. Can or not? I don't want to do too much. So this is what? Expected value of x1 plus x2 quantity squared. Right? So this is equal to, let's do it slowly, x1 squared plus 2 expected value of x1, x2 plus expected value of x2 squared. Right? The means are equal to, now use uncorrelatedness. Now this is by the uncorrelatedness, but by 0 mean, these two are 0. Actually, you only need one of them to be 0 mean, right? But now these two are variances. This is equal to a variance of x1 plus variance of x2. So done for the special case. Okay? I didn't mean to prove this, but I can prove it without making a mistake. So I do it for you. You do the general case. The point I want to make here is that for arbitrary random variables, this could be very correlated. This exercise could be very correlated. We have linearity of expectation. But if we want to consider the variance, we need some condition. Later on, we are going to do exciting theorem related to linearity of expectation. So we take a 10-minute break now. because my professors told me not to start a proof and stop in the middle. So we take a 10-minute break, come back at 7:20. Okay? Take care. I should pause the recording. Hello? Okay, welcome back. We are recording, right? Good. So just now I talked about the linearity of expectation. So arbitrary random variables x1 to xn, we have that the sum of the expectations is equal to expectation of the sum. Homework for proof for homework, okay? So is this useful? So I want to show you that this very simple fact is very useful to prove some rather deep theorems, okay? Now I want to introduce some new concepts, may or may not be new to you, but I want to introduce some concepts that I want to show you that actually this concept of linearity of expectation is useful for us to prove some non-trivial facts, okay? So some of you may have heard of graphs, okay? Graph is not X and Y like graph like that, but okay, it's something else, all right? A graph consists of vertices and edges, right? Definition. A graph, G, consists of two objects, V and E, consists of a vertex set or node set, V, and this graph has n nodes. Each of the nodes is called a vertex or a node, and a set of pairs of vertices or nodes, E. So E is a subset of V choose 2, okay? So for example, if V is equal to 1, 2, 3, 4, and E is equal to the set 1, 2, 2, 3, 1, 4, then we have the graph given by 1, 2 connected, 2, 3 connected, and 1, 4. Okay, so that's a graph. And graph, you can take 3 classes on graphs. You can learn a lot about graphs. And 1/2 of a lecture is not enough to talk about graphs. But nevertheless, we will talk about graphs. Okay, so this is a very simple graph. It's a tree, okay, because there are no loops and so on. Okay, so this is a graph. All right, so this graph, every edge has 2 nodes here, as you can see. So in particular, this is a particular edge, this is an edge, and this is an edge. Every edge involves 2 nodes, no more, no less. So if we want to generalize this concept, we have to do a little bit more, all right? A hypergraph, all right? Okay, so you can think of a graph, right, as 1 and 4 are friends, 1 and 2 are friends, 2 and 3 are friends. But sometimes you don't just have friends, you have groups of friends, right? A group of people are friends. So you want to consider hypergraphs as well. H equals to VE, okay, consists of a set of vertices. This is the vertex set, just like before. V equals to 1 to n. Let's consider a set of vertices V and a set of tuples of vertices or nodes E. Each E in E is called a hyperedge. Okay, so for example, If n is equal to 10, then v is equal to the vertex set 1 up to 10. And we can create many interesting edges. For example, 1, 2, 3, 4, 2 or 5. Okay, 4, 5, 6. So each one of this is a hyper edge in general. And we can have 8, 9, 10, 7, for example. So this is not a regular hypergraph. Okay, this is not a regular hypergraph because some edges have involved 2 nodes, some edges involve 3 nodes, some edges involve 4 nodes. Right? So this is not regular. We want to consider regular graphs, regular hypergraphs soon. Okay. All right. So another definition, before we try to state Erdős result, okay? Actually, Erdős is the one who popularized the probabilistic method. Okay, so, but this probabilistic method is summarized very nicely in a beautiful book by Noga Alon and something Spencer. All right. What Spencer did? I have this book in my office if you're interested. Joel Spencer. Okay, definition. A K uniform hypergraph HVE is a hypergraph if it is a hypergraph, let's say, is a hypergraph K uniform hypergraph is a hypergraph such that if, okay, maybe if is better English, if each E in E contains exactly K nodes or vertices. Okay, so for example, we can consider this case here and modify it slightly. So this is not a K uniform hypergraph. It's some arbitrary hypergraph, but let's say we consider this case here and I modify this slightly. Okay, and let's get rid of this. So this is this object here is this is a what uniform? 3 uniform hypergraph. By the way, 3 uniform is also called 3 regular. K uniform is K regular. Okay, so these terms you hear. All right, why am I introducing all these strange things? All right, because we want to show the power of linearity of expectation. All right. So what we are going to do is the following. Okay. We are going to make a couple more definitions. Now, you have 10 nodes. And now we are only given 2 colors in the world, blue and red. Okay, there are only 2 colors. Okay. Now, then we are going to color each node either blue or red. Okay. We say that a hypergraph, a colored hypergraph, in fact, this hypergraph can be K uniform, can be not K uniform. A hypergraph H is monochromatic. Mono means 1. Chromatic means color. That means 1 color. If all the nodes have the same color. Nodes, sorry, in hypergraph, actually, sorry. Maybe to be precise, right? This is not quite good. And H, E in hypergraph H is monochromatic if all the nodes in E have the same color. So for example, this H here is monochromatic. This is not monochromatic. Okay? Not monochromatic. This is monochromatic. Okay? However, if I use blue for 2, I cannot use another color for 2 later on. So now I'm coloring the nodes. All right. So if I use red for 5, right, I must use 5 here. All right. So I must choose if I want to create a graph that is not monochromatic, right? Then I have to choose my colors in a certain way. Okay, but I'm jumping ahead of myself. All right. Definition. A hypergraph H is said to be 2 colorable if we can color all the nodes or nodes in V so that no H is monochromatic. So I'm allowed 2 colors to color my 10 nodes. Every node is either red or blue. Okay. Now I want to ensure, my goal is to ensure that I can create a coloring of the nodes so that my graph or hypergraph is 2 colorable. That means that this sort of thing I don't like. This edge is monochromatic, I don't like. I want every edge to be diverse. I'm coming up with the term diverse by myself. So diverse is not monochromatic. Okay? So I want to make sure that a graph is 2 colorable. So what is the observation? If H has more edges, it is blank, 2 colorable. Fill in the blank with more or less. If H has more edges, hyper edges, if you wish, hyper edges. If I have a fixed N, fixed K, all right, fixed N, fixed K. N is the number of nodes. K is the number of nodes within each hyper edge. Think of K as 3. Think of N large, all right? So if I have more and more hyper edges, does it make the whole situation more and more likely to be 2 colorable or not? Less likely, right? Less likely to be 2 colorable because I have more constraints. Every edge I want to be not monochromatic. I want to be diverse. Basically, I have like many groups of people, and within each group, I need to have some men and some women. All right. If I have many groups, it is very difficult to assign the genders. All right. So that every group has men and women. All right. So for example, here, how would I assign color? Okay, sorry. This is easily colorable. Okay. So 1 here, if I want to make this not monochromatic, that's what I would do. Then this is not monochromatic already. Okay. Now, how would I assign a color to 4 and 6? This is easy. I will assign blue. 10, I will assign this. 3, I will have to put this. 4, I would have to do this. So now 7, I will have to do this. Right? 7, I'm allowed to do this. And 8 and 9, no problem. So this is 2 colorable. I just showed you a 2 coloring. But now if I have many, many more of these things, right? Hey, am I missing a bracket? Sorry. This should be black. Okay. So if I have more and more edges, then it's not so simple anymore. I cannot use brute force, right? Just now what I was doing was guessing. But if I have many, many more of these edges here, then it's not so easy to color. All right. And please note that if I put 2 is blue here, I must use blue here. If I put that 5 is red here, I must put 5 here. No cheating. All right. So the claim here is that if H has more hyper edges, it is less likely to be 2 colorable. So what is the interesting question? Okay. What is the maximum number of edges I can have to ensure that there is a two coloring? To ensure that a particular graph is two colorable? That is the interesting question. Theorem. This is due to Erdos, 1963 or 64. Okay. Every K uniform hypergraph with less than 2K minus 1 hyper edges, let's just say edges, edges means hyper edges, is two colorable. Oh, okay. Okay. So you may wonder whether this is a good result. Okay, so I can tolerate this number of hyper edges, 2 to the power k minus 1. And I can still find a coloring. I can still find a coloring such that every edge is diverse. Right? This is the claim. So the proof of this involves, can you please exhibit a coloring? Can you please come up with a coloring? Given any hypergraph, can you please come up with a coloring of the edges so that every edge is not monochromatic? That's the claim. Okay? So we are required to exhibit a coloring. But now we have to do the very difficult thing of, you give me a hypergraph, I need to do a coloring. But someone else may come up with a hypergraph and I need to do another coloring. This is too painful because I need to somehow tailor my coloring to everybody's hypergraph. Very painful. So Erdos came up with a probabilistic method to show this. Now, before we do the proof of this, let me just do a remark. Is this optimal? Okay, is this result any good? Maybe it is very bad. Maybe you can do 3 to the power k. You can, maybe some people can say, oh, I can for every hypergraph with 3 to the power k edges, hyper edges, nevertheless, I can find you a coloring. This is not true. Okay, this is almost as good as you can get. Why? Erdos, 1964, showed that there exists a K uniform or K regular hypergraph with O k squared 2 to the k hyper edges or edges, same thing, that is not two colorable. So this is very small. This k squared is very small compared to the 2. So it says that this base here, this 2, cannot be improved. You cannot do 2 plus epsilon. 2 plus epsilon power k is not possible. The 2 is optimal. You can possibly improve on these sort of things, polynomials in front. If you can improve on the k squared, then you'll be quite famous. Okay, so this is Erdos' coloring result. Okay? And the proof of this theorem, the 1964 one is very difficult, but the 1963 one we can do now. Do people understand the statement? The statement of the result. So the statement of the result says, we're not going to prove this remark thing. The statement says that, okay, you give me any K uniform hypergraph, no matter how many nodes, I don't care. All right, as long as it has fewer than 2 to the power K minus 1 hyper edges, then I can find you a coloring, or 2 coloring, such that every edge is not monochromatic. Every edge is diverse. Many colors, 2 colors. Okay, and as you can see, if I increase the number of edges here, right, it's difficult, going to be more and more difficult combinatorial optimization problem, right? Okay, so ready? Exciting? Ready? Okay, proof. We proved this in 1963 one. Okay, so now someone is going to give me a graph. Let H equals to VE be a K uniform hypergraph with less than 2 power K minus 1 hyper edges. Sorry, I'm getting a bit lazy. Hyper edges means edges, okay? Okay, so what am I going to do? I need to exhibit one coloring, at least one coloring, so that every hyper edge is not monochromatic. Right? That's my job. So my job is too difficult. I will say, oh, let's randomly do it. All right. So color each vertex V in V, each node that is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. With one of two colors, blue or red, with equal probability. Okay. Now, so that's what I'm going to do. You give me a graph, I'm going to color uniformly at random every edge. You look at, every node is going to be assigned red or blue with equal probability. Okay, define now the random variable xe. Okay, for every E in E. Define the random variable given by the following. 1, 0. E is monochromatic. And else. So I'm going to define a random variable, E. This E, xe is 1 if that particular edge is monochromatic. So, okay, so for this particular coloring, all the xe's are equal to 0. Right? All the xe's are equal to 0. But if there's one particular edge here that is uniform in color, monochromatic, then the xe is equal to 1. Right? So this is a simple random variable, right? Okay. Consider the new random variable x equals to some E in E of xe. Consider this random variable. Now, let's look at all these random variables inside the sum. Are they independent? No, far from it. Right? So suppose I've got a hyper edge like this. 1, 2, 3. And 2, 3, 4. Okay, these are my two hyper edges. And I know that this hyper edge xe is equal to 1 because it's monochromatic. Okay, but for this I already know that it is like this because the 2 and 3 must be of the same color. So I already know some partial information. I already have some partial information about xe prime. All right, that 2 of its nodes are red in color. So the xe and xe prime are not independent because knowledge of the colors of 2 and 3 give me some information about the entire likelihood that this thing is monochromatic. Maybe we need a little bit more, sorry. Maybe we need that this is a bit larger, say 4 here, and this is monochromatic. 2, 3, 4, 5. Okay, and I have red here, red here. Now, xe prime is very likely to be monochromatic now. Okay, so xe, because there's overlap here. So xe and xe prime are far from monochromatic, are far from independent. Okay, they are far from independent. All right, now let's do the following. What does this random variable mean? This random variable denotes the total number of monochromatic edges. Because you are summing 1. Every time you encounter a monochromatic edge, you are adding 1. It's the total number of monochromatic edges. edges in H. Okay, let's compute some simple things. Expected value of XE. Okay, what is the meaning of this? What's the meaning of expectation? 1 times, how do we do this? Expectation means you take this number, multiplied by the probability of this event. E is monochromatic, okay, plus 0 times probability, E is not monochromatic. Okay, so this goes away. Right? The 0 times anything is 0. Okay. What's the probability that E is monochromatic given our coloring scheme? What was our coloring scheme? Color each vertex with one of 2 colors with equal probability. So the probability that E is monochromatic is probability E is all blue plus probability E is all red. Everything is done every coloring is done in an independent fashion, right? This 1 over 2 power k, because every edge has k nodes. The chance that all of them are blue is 1 over 2 times 1 over 2 times 1 over 2 k times, plus 1 over 2 power k, which can be written as 2 to the power of what? Minus k plus 1. Let's just write it in this way. Everyone agree? Agree, right? Simple calculation, right? Hence, by linearity of expectation, expected value of x is equal to sum over E in E. Expected value of XE is equal to the cardinality of E. Okay, let's just write this as English, all right? Number of edges in H multiplied by 2 to the minus k plus 1. Because this object here is exactly equal to 2 to the minus k plus 1. From the previous calculation, right? So I've just computed this object here. This object here is exactly 2 to the minus k plus 1, and I put it here. And the sum, we are summing over the total number of edges. So the sum here takes care of the number of edges in H. Right? Correct? Any questions? Okay. But we assumed that the number of edges in H is less than, strictly less than, 2 to the power k minus 1. That's what our assumption says. That's our assumption. Multiplied by 2 to the minus k plus 1. Right? No cheating, right? This is nicely giving us 1. So what do we conclude? What do we conclude? In conclusion, by our coloring scheme, expected value of x is less than 1. Okay, but what is expected value of x written as? Well, it's 0 times p of 0 plus 1 times px of 1 plus 2. Let me write one more. 2. This is the meaning of expectation. You agree? This is the exact meaning of expectation. Okay. Since expectation value of x is less than 1. From the above, in conclusion, expectation value of x is less than 1. Right? What can we conclude? Px of 0, this probability mass at 0, must be bigger than 0. Do you know why? Suppose otherwise. Suppose this is equal to 0. Okay? That means, suppose this, okay, why? Suppose, to the contrary, px0 equals to 0, then expected value of x, sorry, not enough space. Expected value of x will be equal to, well, 1 times px of 1 plus 2 times px of 2 plus so on and so forth. Right? This will be at least equal to 1. At least 1. Right? Because the px1, px2, all these things sum up to 1. X bigger than 1. Because there's no mass at 0. Suppose to the contrary, there's no mass at 0. Then because this sums up to 1, this sum here must be at least 1. Right? Because of this leading term here. Okay? So this contradicts this. So we must have this. Well, what does this mean? What does this mean? Okay. The fact that px0 equals the probability that x equals to 0 is greater than 0 means in English that the probability that H has 0 monochromatic edges is positive. Hence, the probability that H is 2 colorable is positive. X equal to 0 means exactly that H has 0 monochromatic edges, which is the same English statement as H is 2 colorable. H has 0 monochromatic edges means that H is 2 colorable. That means that in our random coloring of the edges, of the nodes, of the vertices, there is at least one configuration that ensures that all the nodes in each of the edges is diverse. Each of the edges is diverse. We have no monochromatic edges in at least one of the coloring. Because if we had, if we color in the way that we do, and all the edges are monochromatic, then X would be equal to 0 with 0 probability. There's a logic here. Let me repeat the whole argument. This is for enrichment, to show you that linearity of expectation is very powerful. But there's a logic here that is very powerful if you want to prove existence of things, all right? Because usually proving existence of certain objects is not easy. Here, what have we done? We have in fact said, we have in fact done the following. Now, I cannot actually determine if there is a student in this class whose weight is less than 45 kg. I cannot measure all the weights. So I put all the students on the certain weighing scale, and I noticed that the average is less than 45 kg, for 40 kg. Did I say 45 or 45? 40 or 45? Whatever, X kg. Right? I want to determine that there exists a student whose weight is less than X kg. I put all the students on a weighing scale, and I divide the total weight by the number of students. And I noticed that the average weight is less than X kg. That means there must exist at least one student whose weight is less than X kg. The same principle here. So let's go through the principle again. Theorem. Every K uniform hypergraph with less than 2K minus 1 edges is 2 colorable. All these terms are, hopefully you remember. And this 2 here is tight. You cannot improve to 2 plus epsilon. So first, we let H be any arbitrary K uniform hypergraph with this number of edges. Okay. Now, since we are not so smart as to be able to color our friend's hypergraph, every friend will give us a different hypergraph. We'll say, oh, whatever hypergraph you give me, I'm going to color every vertex or node uniformly with probability half red, probability half blue. Okay, that's what this line means. Okay, now we define the random variable xe is divided by this. So if I look at the H and I see that it's monochromatic, the random variable is 1. Otherwise, it is 0. I create this new random variable that represents the total number of monochromatic edges. This English is not good. Edges in H. Okay. So let's compute. So these XEs are far from independent. And that's the power of the linearity of expectation here. Even if the XEs are not independent, I can do linearity of expectation. So I calculate the expected value of XE, which turns out to be the probability of monochromatic E. Now, E can be monochromatic if and only if E is all blue or all red. The chance that it's all blue is 1 over 2 power K. The chance that it's all red is 1 over 2 power K. So this adds up to this. Hence, by linearity of expectation, expected value of E, of expected value of X, you can pass the expected value inside here. And we already calculated this. So we put it here. And the sum here is the number of edges in H. Okay. So after some cleaning up, you see the expected value is strictly less than 1. In conclusion, the expected value is strictly less than 1. However, X is a random variable, is an integer valued random variable that can only take on these values. Okay, that's important. X is an integer valued random variable that can only take on values 0, 1, 2, 3, 4 up to a certain number. In particular, it can take on the values 0 and 1. Okay? So because X is this type of random variable, its expectation is given by this. Okay. Since expected value of X is less than 1, since the average is less than 1, there must be some mass at 0. Because if there were no mass at 0, the expected value is actually at least 1. Okay, this is the proof by contradiction. So the probability that X is equal to 0 is bigger than 0. What is this meaning? It means that the probability that H has 0 monochromatic edges. 0 monochromatic edges means that it is too colorable. It's positive. Hence, there must be a certain coloring. Among my colorings, how many colorings are there? 2 to the power of n colorings. There must be a certain coloring that results in every H being not monochromatic. Done. So this is a powerful proof technique that underpins a lot of the probabilistic method. This is the proof technique for my area of research, which is also known as information theory as well. We cannot construct a code to do transmission. So we just randomly choose a code. And it turns out that random codes are very good. Same idea. Okay. Any questions? Any questions from the Zoom people? By the way, I want to say something. I decided how to conduct a quiz. The Zoom people have to come to the class. Everyone is going to do the quiz in this class. We have only 47 people, 46 or 47 people. So this classroom can accommodate. We are going to do in person. Otherwise, it's too complicated. I tell the Zoom people now first. So you have to show up. And everything is okay. We have the good enough room. Okay, we don't need to rush. Any questions? Yes.
For this proof, it's just a combinatoric proof in disguise, right? You're just using probability to make it look nicer.
I don't know how to answer that question. Because there's nothing combinatorial to this.
You imagine that every case that can happen is just 1 out of that.
2 to the n. 2 to the power n. Yeah. Yeah. But then I exhibited configuration, a coloring of the nodes such that if I have fewer than 2 to the power k minus 1 edges, hyper edges, then each one of the hyper edges will not be monochromatic. Right? This is not a combinatorial proof. This is actually a probabilistic method proof. Okay. I don't really know about combinatorics. Yeah. Too difficult for me. I want to talk about something very important. The next thing I talk about is super important. And I can guarantee you, with probability 1, there will be a question on the first quiz on this. If you look at my last 3 quizzes, right, on quiz 1, every quiz 1 will have a question on conditional expectation. I want to tell you that conditional expectation you know very well because it underpins a lot of important things in probability. Okay, so the next topic is conditional expectation. I already told you what is expectation. But now we're going to talk about conditional expectation. All right. Say x, y are discrete random variables with probability y bigger than 0 for each y. Okay, so this is the probability y equals to y. Yeah. Every one of my quizzes and every one of my exams has a question on conditional expectation. I expect people to know this. And people still do not know this. Maybe because my teaching is crap. All right, so let's define the conditional expectation of the random variable x given event y equals to y. Is defined as, and is written as conditional expectation of x, y equals to y. What is the meaning? Sum over all possible values of x, p, x given y, x given y. And this object here is well defined. It's a conditional probability. It's a joint probability divided by the marginal, which is always positive, as assumed above, exists for all xy. Okay, so that's the definition of conditional expectation. What do I want to say? Okay, I don't need to say this. So this is conditional expectation of x. I want to highlight these words here. Conditional expectation of x given event. All right, it's given an event. Y equals to y. Right. Now we have another important concept. The most important concept today. Conditional expectation of x given random variable. We're going to talk about the conditional expectation of x given random variable y. Just now we were conditioning on what y was. Y is equal to little y. Now we are conditioning on a random variable y. What does this mean? Okay, to talk about this, I need to define some other auxiliary quantities. Let's define gy, a function of y, to be the expectation value of x given y equals to y. We already talked about this just now. So this quantity is exactly this quantity here. Okay, this quantity is exactly this. Note that if I vary the little y, if I change, very ugly. If I change the little y, I change the value of the conditional expectation. So if I change this y here, I change this value. So this is a function of little y. Get it? We will do multiple examples later on. So one more time, conditional expectation of x given an event is given like this. Okay, where this is the conditional probability. And we assume that the denominator is bigger than 0 so that nothing is, we don't have to divide by 0 error. So this is a regular expectation. Okay, we have seen this before. We want now to go forward to talk about conditional expectation of x given a random variable y. different concept. To talk about this, let's look at this function here as a function of little y. And this is nothing but, we can give it a name, gy. gy. Okay, so if I change the y, I change the value of this conditional expectation. So this number here, this gy is a number, a real number, right? And in particular, gy is a function of y. Okay. Everyone got it? As I said, this is the most important concept today. Right. So now we can talk about the following. Consider G capital Y, where Y follows the distribution or the PMF PY. So just now I talked about the fact that you have a random variable and you can create a new random variable, the H thing. Just now you saw X, you can create a new random variable HX. You saw this, right? So now I have a function G. There's a function of Y. I'm going to stick in a random variable capital Y. So this makes G of capital Y a new random variable, right? You think of the function G as a function of Y. You stick in Y random variable. You create a new random variable. You created a new random variable, gy. Okay, definition. The conditional expectation of random variable x given random variable y is gy defined is, okay, maybe the right way to say this is expected value of x given y equals to gy. So the conditional expectation of a random variable given another random variable is a random variable. And that random variable is G capital Y. Okay. The conditional expectation of a random variable x given a random variable y is a function of y. Note, the conditional expectation of x given random variable y is a function of y. Okay, this is perhaps the most mind-boggling concept today. The first time I saw it, I can tell you the first time I saw it, it's incredible. Why? Because you think of expectation as a number, right? Expected value of x is 5. Expected value of x is 10. Now, indeed, if you talk about this object here, condition on an event, this is a number, 5, 10. In general, it's a function of little y. But if I create this definition here, the conditional expectation of random variable x given random variable y, this is a random variable. Once I talk about given random variable y, then expected value of x given y is a function of y. Okay, this is f power n is function. Okay, I don't like to write so much. So this is you need some time to let this sink in. Okay, so this is a function of y. Let's prove some properties, and let's do an example. Okay, the first and most important property is the following fact. This fact has two names: law of iterated expectations. Some people call it the tower property of conditional expectation. Now they mean the same thing. Tower property sounds more sophisticated, right? Okay, what does the tower property say? Expected value of, okay, so we have this object here, expected value of x given y. Note that this is a function of y. All right, any function of y is a random variable. The inside is a random variable. So it's also a real valued random variable. So now there's nothing stopping us from taking its expectation. There's the outside expectation. There's nothing stopping us from doing this, right? So, okay, the claim, the Tower property says the following. You recover the value of expected value of x if you take iterated expectation. Iterated means because there are two things. Iterated this and this. Oh, sorry, you cannot see this. Iterated this and this. That's why it's called iterated. Okay, tower. Why is tower? Why is it called tower? Because this looks like a tower here. This first level, second level of the pagoda. Tower property. Okay. So this is what we will prove. I mean, this proof is a matter of making sure you understand the definitions. Law of iterated expectation. Okay. Proof. Let's start at the left-hand side to see if we can recover the right-hand side. Now I'm going to do this for discrete random variables only. Otherwise, too painful. So this is a function of y, right? All right. So this is the expected value of g of y, where g is this above function. Okay. So I'm just rewriting, and this expectation is with respect to y. Just now I already said something. There are two ways of taking expectation. You can go and do, sorry, this is discrete, right? You can do, okay, you can find the distribution of y, p, y, y, g, y. This is one way. Or you can find let's call it z. You can do z, p, z, z. Right? There's two different ways of doing expectation, but we will do it the first way. The second way is too painful. Okay. So what is the first way? The first way is the following: is sum over all possible values of y, gy, py, y. Understand? That's the meaning of expectation. This is the simple way of writing expectation, right? So this is going to be sum over y. What is gy? Aha, gy is this thing in red. See, I'm not cheating here. I'm taking this exactly, putting here. Am I going to do this correctly? Okay, I'm going to do this correctly. Okay, and this is exactly gy, py, y. Okay. Now, what is this thing here? This is the conditional expectation of x given event y equals y. So this is given by the formula. Maybe we write this x, px given y, x given y. Right? So, what can we do now? What can we do now? We can move this x outside and move the y inside. Px given y, x given y, py, y. Right? And now, oops. Now what can we do? We notice that the inside is the joint distribution, because this is by Bayes' rule, right? Bayes' rule says that, okay, we can get the joint here. Right, because x given y and y, you can merge them together to get a joint distribution. Now you marginalize this out. You take away the y, you recover the x. This is called marginalization rule, I think. Undergrad probability, Pxx. And this is expected value of x as desired. So this is equal to right-hand side. Okay, so in order to understand this, you need to understand definitions. All right, and this is so important. I want to say it one more time. Left-hand side is equal to the expectation value of this object here. Gy is expected value of x condition on y equals to y. Sorry, this is this. Okay, that's the gy. All right, so we are going to write this out in its full form, which is this. This is the expectation value of gy. Gy, pyy. But what is gy? Is exactly expected value of x given event y equals y. Pyy here. What is the definition of this? This is the average over x when the distribution of x is constrained to be y equals to y. So expected value of px given y, x equals to y. Px given y, x, y, as follows. Next line, we swap the differences, we swap the sums, and we can do this, no problem, finite, finite. X is outside, x can be brought outside, y can be brought inside. Here, this thing here is a joint distribution. And this by marginalization, take out the y. And we get this as desired. So this is the tower property, okay, for the finite case. For the general case, I think not very difficult to generalize this, but we're not going to do this. Okay. Now, all this is very abstract, right? You will complain very abstract. So let's do an example. Let's change color. Okay, example. This color not nice. This example is in Gallager's book as well. Any questions here on conditional expectation? We don't need to go fast. Any questions on conditional expectation from the Zoom people? What is the meaning of less? 实践? Maybe it's a long time ago. I was asking a question. Maybe. Any questions on conditional expectation? If not, I want to do a cool example. I can tell you that last year's quiz is roughly the same example here, but everyone stumbled because I changed a little bit. They forgot the concept of conditional expectation is a random variable. Okay, now let x1 be the outcome of the phase outcome of the first toss of a six-sided dice. Okay? So x1 can only be from 1 to 6. And let x2, unsurprisingly, be the outcome of the second toss of a six-sided die. So six-sided, you know, right? If I tell you eight-sided, then we are going to be very confused because we haven't seen an eight-sided die before. All right, so six-sided, everyone has seen before, right? So let's see the random variable s is x1 plus x2. Oh, terribly simple, right? Very simple. X is just a sum of the sum of the outcomes of two dice. Hey, let's think about this before we do any math. You toss two dice. You can get the numbers 2 to 12, right? You cannot get 1, sorry, unless you go and smash one die. You can get the numbers 2 to 12. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Which is the most likely? 2? Actually, 2 is the least likely together with 12. For 2, you only have for 2, you only have one outcome, 1 plus 1. For 12, you only have one outcome, 6 plus 6. Right? So which one has the most outcome? It's in the middle, right? 7. 7 has the highest chance, okay? Anyway, so S is a random variable that takes on values 2, 3, up to 12. Okay, let's just understand the story first. But this example helps us to illustrate the concept of conditional expectation. So now let's condition, okay, on event S is equal to J. 1, 2, say J is a number, say the sum, all right? Cannot. I think there's a typo here. S cannot be 2, cannot be 1, right? It must start from 2, right? sorry. Okay, so suppose that we know that the sum is 2. Okay, later we deal with the rest of the numbers. Suppose we know that the sum is 2. All right. What is the distribution of x1? The sum is 2. x1 can be 2 or not? Cannot, right? x1 can only be 1, right? So now let's do one more. Say s, the sum is 3. Then what are the possibilities of x1? 1 and 2. Count slowly. Because you still have an x2 to deal with, all right? x2 to deal with, right? So suppose s is equal to 3. S is equal to 3 here. x1 is uniform on 1 and 2. Because there's nothing to different, these are two independent tosses. I forgot to say it's independent, but they are independent, okay? Not independent cannot do. Okay, so in general, x1 will be uniform from 1 to j minus 1. That is the distribution of x1. Condition of the event that s is equal to j. Okay? This requires a moment of thought. But the sum can be other things. Yep, okay, correct. Now, you see, the sum, as I mentioned, can be other things as well. Right? The sum can go from 8 to 12 as well. These are the high sums. Now, suppose, right, the sum is 8. What is the distribution of x1? Actually, I don't need to talk about the distribution of x2. It's symmetric, okay? That's why I talk about x1 only. Suppose j is equal to 8. Can x1 be 1? Cannot, right? Not enough, right? x1 must be at least 2, right? Because 2 plus 6 is equal to 8. X1 cannot be 1. So I gave a question like this. There's a lot of things to think about, actually. You need to know how to split up this s equal to j into 2 parts. Right? If s is equal to 8, x1 cannot be 1. It must start from 2. If s is equal to 9, x1 must start from 3. Right? Etc., etc. I will not belabor the point, but this will be j minus 6 up to 6. And by uniform, j minus 6 up to 6, I mean that this is a uniform distribution on all these numbers. Okay? Just like, okay, e.g., if s is equal to 9, then x1 can only be uniform on 3 to 6. Understand? Okay, e.g. All right. So what? All right. So let's consider the expectation value of x1 condition on s equal to j. Now for small values of j and for big values of j, say j less than equal to 7 and j greater than 7, because these are the two different cases. Okay, so this case here pertains to this case here. Okay, j is less than equal to 7. Okay, let me be a bit more, let me not be so lazy. Okay, j between 7 and 2, j between 12 and 8. What is the expectation value of x1 given that s is equal to j? Okay, the distribution of x1 is the following. So the PMF of x1 condition on s is equal to j is 1 to up to j minus 1 uniform. Okay, so for a uniform distribution, the mean is in the middle. All right, so you got 1 plus j minus 1 over 2. Understand? You take the first, you take the last, you divide by 2. Got it? That is the expectation value of x1, because the distribution of x1 is given by this object here. So what is the mean? The mean is 1 plus j minus 1 over 2. Agree? Any questions? You look at this distribution here. You take, that was the mean. The mean is here. 1 plus j minus 1 divided by 2. Okay? Now, similarly, here, we are going to take j minus 6 plus 6 over 2. Understand? Now, let's write this properly. So this is an example of this sort of things in action. This is in Gallager's book. This is j over 2. J over 2. I just simplify. Okay, so that we don't leave so many things around. Okay? Simplify. Thus, let me write a statement. If we consider the random variable y, which is equal to expected value of x1 given s. Okay? This is a discrete random variable. What are the values that it takes on? All right, it's a discrete random variable that is a function of s through j, okay? Through the value s takes on the value j, okay? But it takes on values, it's a random variable that takes on values, basically 2 over 2, 3 over 2, 4 over 2, all the way up to 12 over 2. Let me do a little bit more. 11 over 2, 12 over 2. Understand? Because y is exactly this random variable here. What are the values that it takes on? It takes on these j values, j, okay? It takes on these values, j over 2, j over 2. So this can be summarized, this line here, let me move this down a little bit. Okay, this line here can be summarized as regardless of what is the value, of j, be it in the low interval or the high interval, this is equal to j over 2. Thus, y, a new random variable, equals to x, expected value of x given s, is a discrete random variable that is a function of s and takes on values j over 2 for j running from 2 to 12. Right? Okay. So, in other words, py of j over 2 is equal to ps of j when j runs from 2 to 12. That's the distribution of the newly created random variable y that is a function of s, this random variable here. Okay, it takes on the values all these values. These are values j over 2 for j running from 2 to 12. Okay, now let us consider expected value of x1. Now, if I tell you toss a die, right? What's the expected value? 3.5. 1 plus 6 over 2, 3.5, right? Let's do it the long-winded way, okay? Let's use the tower property here. This is the tower property which we proved just now, okay? So this is nothing but, okay, this is an expectation value over s, where s takes on values j running from 2 to 12, and this is py j over 2. Okay, so this is nothing but given by, this is j over 2, because the values of s, these values here. Okay, so this is nothing but sum j running from 2 to 12 of j over 2, but py j over 2 this, I'm using this fact here, is nothing but PSJ. So this is half of the expectation value of S. S is the sum. The sum of two dice has expectation value 7. 7/2. Okay. So here what I've done is basically I've calculated the expectations as a function, conditional expectations, conditional events. Next, I created a new random variable y. And y, this random variable y here, is now a new discrete random variable that is a function of S and takes on values given by all these numbers that are from 2 to 12 in steps of half. Okay? And y is related to S just by the fact that y is equal to S/2. So actually, you can say that y is equal to the random variable S/2. Okay? This is actually easy to see, right? Intuitive. So now we make use in the last line of the Tower property. Okay? This is the Tower property here. The outer expectation is an expectation value over S. Okay, now we are just using basically the definition of expectation. Okay, right? This is nothing but the definition of expectation. This transition here. Okay, and this is equal to this because PYY is equal to PSJ. PYJ/2 is equal to PSJ. And that's how we arrive at this somewhat tautological result going in circles. But I just wanted to show you all the different computations in between. And this is also explained in Gallager. Okay, so this is just a Gallager example. You can look at this. And actually, you can look at last year's quiz 1. Last year's quiz 1, where I asked the students to do this calculation. But now, instead of throwing a dice from 1 to 6, we are generating a uniform number from 0 to 1. Same thing, right? Now, instead of discrete, continuous. Then a lot of people were very confused because there are so many ranges to deal with. Just like here, you need to know that you should split into this range, 2 to 7, 8 to 12, right? So I asked them to do a bunch of calculations and everyone just do some very funny thing. But actually the concepts are not difficult, all right? You need to know that conditional expectation, what does it mean? The easiest way to think of conditional expectation like this sort of object is to first condition on a particular event S equal to J. That is something that we are familiar with because expectation, we think expectation as a number, right? But then if we let this random variable be Y, then Y precisely takes on the values that those numbers are. Okay, just like here, Y takes on values J/2. Because the expectation value can only take on this J/2 for J running from 2 to 12. Basically, the numbers from 1 to 6 in steps of half. Okay? Right. This is the most important concept. And you will play with this in the homework, guaranteed. And you will play with this in the first quiz and the exam, guaranteed. Okay? I will show some examples here. I will ask you to do some intermediate calculations. Now, I want to talk about this one last concept and we can call it a day. Next time, we will do something else. Moment generating function. It's called MGF. Okay, in a good undergraduate class, you have seen it before. Okay, so X is a random variable. Okay, we can talk about the function h of x just now, the transformation of a random variable. We can talk about the transformation e to the rx. All right, here r is some real number, in which case the expectation value of h of x, all right, is known as the moment generating function of x. Okay, and we give this a name. We call this gx of r, which is expected value of e to the rx, equals to the following: e to the rx fx of x dx for the continuous case. Okay, So this is the moment generating function. Why is it called moment generating function? Because it generates the moments, as we will see shortly. Now, people in electrical engineering, in mechanical maybe, they often see these sort of things and play with this. This is the Laplace transform of this signal. Actually, Laplace transform has a minus. The usual way that I learn. The American way has a minus. Okay, the American way has minus infinity to infinity. The British way only has 0 to infinity. I was educated in both Britain as well as America, and slightly different. Okay, but this is the, I don't know, this is the, without the minus is the negative Laplace transform or whatever. But this is the American way. Okay, so what I want to say, why is this called moment generating function, and why do we even care? All right, this is for the continuous case, and so for the discrete case, we have this sum over all possible values of x, e to the rx, px of x. This is the PMF, and this is the PDF. Okay, so some of you may have seen this before. So sometimes we do talk about a cumulant generating function. This is very useful. The cumulant generating function is log gx of r. Okay. All right. So this is also very useful in the theory of large deviations, which we will talk about next time. So here's a fact. If gx r exists in a neighborhood around 0, note that expectations need not exist. I already said. Note that integrals need not exist. All right. So for some values of r, this may exist, this may not exist. This one. Exist means finite. So if you can find a neighborhood around 0, a small neighborhood around 0. So this is an analysis thing. This is 0. You can find a small neighborhood around 0 of r. So r inside this neighborhood. This integral converges. It's finite. Then we are very happy. Okay. Then here's a fact. Its derivatives of all orders exist in that neighborhood. In that neighborhood. MBD is neighborhood, okay? And in particular, let's consider the first derivative of gx of r. So that would be d by dx of this thing here. Right? It will be d by dx of this thing here. Okay, so suppose we can differentiate under the integral. So we can move this inside. R, sorry, d by dr. Thank you very much. Otherwise, we are in trouble. D by dr of e to the rx fxx dx. So we can do this. Suppose we can move this in. It shouldn't be a problem. It's not a problem because everything is positive. So r, e, r, okay, sorry, it's not r because we are differentiating with respect to r. So x, e, r, x, fxx dx. Okay, so this is the first derivative. Okay, this is the first derivative. And if we set the first derivative to be equal for r equals to 0, then you can see that we recover this part, which is nothing but the expectation value of x. Okay. Now, I'm not going to do this, but more generally, if you take the kth derivative, d by dk by drk of gxr, and you set it to be equal to 0, then by successive differentiation of the e to the rx function, you will recover expected value of x to the power k, which is the kth moment of x. Thus, this is called the moment generating function, because if I successively differentiate k times and I set the parameter to be equal to 0, then I recover the kth moment. That's why this is called moment generating function. It generates the moments. Okay? So this is a thing for you to check. I did the first one. You do others. Okay, I did the first one. You just successively differentiate this guy here. Then you bring down more and more x's, right? You bring down more and more x's, and that's the proof, okay? I'm not going to do this. Next time, we will need this fact. Okay. Say x1, xn, mutually independent. Okay, but not necessarily identically distributed. They're only independent, mutually. Okay, then create this new random variable x1, xn. Create this new random variable, the sum. This is going to be super important for us. Next lecture, we are going to talk about something that makes a lot of people confused. And that is the laws of large numbers. Okay, convergence of random variables. It's going to make people a bit confused. So I have a way to explain it, a way to explain convergence of random variables so that people are not so confused. The first time you hear about convergence of random variables, you will be confused. All right? But I try my very best to explain the differences in convergence in probability and convergence almost surely. Okay, that's what we are going to talk about next time. And we're going to talk about things like that, sum of random variables, all independent. Okay? In proper courses on probability, the first course on probability will be all focused on the sums of independent random variables like this. The second course will be on dependent random variables. Okay, but this is a simple object. All xi's are mutually independent. Let's consider the moment generating function of Sn, denoted by G as nr. So that's nothing but expected value of e to the r Sn, okay, which is expected value of e to the r x1 plus xn, right? So we can rewrite this as expected value of the product of I running from 1 to n e to the r xi. Because the product of these e things, you basically sum the exponents, right? Okay, because the xi's are mutually independent, these people here are also mutually independent. These guys here are also independent. So this becomes product expectation. You can move it inside. Aha! But now we notice that this is equal to the product of the moment generating functions of the xi's. So the point here is that if I have two random variables that are mutually independent, no, they are mutually independent, then their moment generating functions multiply. This is the same idea as linear systems in electrical engineering. You have this signal and this impulse response. You pass the signal through the impulse response, you get convolution. And you take the Fourier domain, you get the product of the Fourier transforms. This is the product of the Fourier transforms here. Same thing. Okay? And in the special case, if the xi's are IID, so in addition to being independent, they are identically distributed, then G of SNR is equal to G of XR power n. IID, say, let me make this look nicer. If the xi's are ID with common distribution fx, common PDF or distribution, whatever, then we have the following result. So because the product here just becomes an n-fold product. Yeah, if all the same distribution, so all these guys here are this, and this product here gets power n here. Okay, so that is all for today. I'm not going to talk about the last page because that is a different topic. And my professor told me never to start the topic, a new topic, at the very end when people are very tired. So, what did we talk about today? I already forgot. We talked about too many things. We wrote 17 pages. At least I wrote 17 pages here. You can see here. Okay. So we talked about the fact that you need to submit homework 1 today. before the midnight. But a lot of people have already submitted, I saw. So enthusiastic. Maybe you need more questions. And you need to read 1.4 to 1.6 of Gallager's book and my notes, lecture notes 2 for that hypergraph example. We talked about what is meant by expectation. This is the usual definition of expectation that you have seen before. Undergrad definition. Okay, undergrad. Okay, expectations need not exist, even in the discrete case, if you have infinitely many sample points. We talked about the fact and we proved the expectation can be written in the layer cake representation, like this. Okay, and we proved this both for the discrete case as well as the continuous case with a little bit of tricks here and there. This is not in my notes. All right, so, but I'll upload this, so these notes anyway. So we did mainly focus on a case where X is non-negative everywhere. But if X has positive and negative sample values, we have to do a little bit more work, but it's fine. All right, we have to be a bit more careful in the bookkeeping here. Okay, then we talk about the existence of the expected value. If X is a random variable with positive and negative sample points, then you can talk about its existence. The expectation value exists if these two integrals converge. We talked about, very importantly, random variables as functions of other random variables. Okay, and we talk about variance. We talk about variance expectation. We talk about convolution of independent random variables. Okay, and the fact that the distribution, the PDF of the newly created random variable is a convolution of the previous PDFs. And in particular, independence is super important here. We talked about linearity of expectation, leading to an exciting theorem. We talked about the fact that if you have uncorrelated random variables, then their variances sum in this way. Okay. Okay, so we talk about the probabilistic method in which we want to consider a hypergraph, and we want to understand what is the limit on the number of hyper edges such that the graph is too colorable. And we prove this result by Adosh using the probabilistic method that says that every k uniform hypergraph with less than 2k minus 1 edges is too colorable. Okay, so we talked very much, this is very important, conditional expectation. Conditional expectation, two types. One is condition on event. Another type, condition on random variable. Condition on event is relatively simple. You get a number. If you condition on a random variable, you get a new random variable. Okay, super important distinction. We prove the law of iterated expectation or the Tower property. Okay, this is a matter of bookkeeping, and I will not belabor the point. So I will also emphasize this example where we have x1, x2 independent outcomes of a toss of a 6-sided die. So the sum can only be from 2 to 12 if you think about it. And we successfully condition on various events s equals to j. The j can only be from 2 to 12. And we figure out what is the expectation value of x1 given s is equal to j. And in general, you can expect that what's the average value of x1 if you observe the sum to be j? It must be j over 2. But this is a careful calculation that we did. Then we did a careful calculation on the expected value of x1 through the conditional expectation here. Okay. Then we talk about, lastly, we talk about moment generating function, which is just a special function here, special h function that we plug into the expectation formula here in order to get this. Okay. What is the good thing about this object? Well, it generates the moments. In what sense? If you differentiate with respect to r one time, you'll get the first moment. If you differentiate with respect to r k times, you get the kth moment. Okay, and we prove, or we didn't prove it, it's just a calculation. If all the x's are mutually independent, and here mutually independent is important, uncorrelatedness is not enough. Okay, then the moment generating function of the sum is the product of the moment generating functions. So these are important facts that I summarized for you today. Oh, Ma Zhengtian asks, what exactly is a moment? Snapshot of the moment, the kth moment of x is expected value of x power k. Ma Zhengtian, I think this is the correct definition. Sometimes in applications, we are interested in another definition. I tell you one more thing. The kth, sometimes we are interested, we need to do the following, okay? The kth absolute moment, okay? Sometimes we need to talk about absolute moment. Is absolute this k. The third absolute moment is not the same as the third moment. It's not character function, it's characteristic function. The characteristic, sorry, the Zoom people are asking me questions, but I think you are also interested, of x is expected value of e to the I tx. So this is the, just now I gave g, right? So I do not know characteristic function is g, maybe I could h of t. The characteristic function is the Fourier transform. Okay, the characteristic function, maybe the Fourier transform is not t, maybe you know s here. T looks very funny. This is the characteristic function. So the characteristic function is very useful. Again, it can generate the moments, but you need to keep track of, because when you differentiate this, right, you get some i's, you get some imaginary parts. And then if you continue to differentiate, you will get something like -1 power k. So you have to be careful about all these things. It's called characteristic function, not character function. Okay? So all these are sort of related. Any more questions? To the Zoom people also?
Just now you mentioned that, just slightly above, you mentioned that mutual independence is required to get this.
Yeah.
But the part where it says the expectation of a product is equals to product expectation only requires uncorrelated.
No. No, not quite, because this is an arbitrary function. Okay, if you are talking about yes x y like this, then uncorrelatedness is enough. But here we are talking about arbitrary functions. We are taking functions of this. I don't think it's enough. We need mutual independence.
So
Here we are taking an arbitrary function of xi's, or special function.
So the crux is that the e to the power r xi is only mutually independent if xi is mutually independent.
Yeah.
Uncorrelated.
Uncorrelated is only for this part, for without passing this through a function, I believe. Yeah. Let's erase this. Okay, the people, Yanke, did I answer your question, Yanke? Probably. Zheng Tian, I think I answered your question, right? Okay. Anyone else has any questions? You can ask me here also if you want. Okay. Thank you very much and good night. Have a great weekend doing my homework.